Tonight, we're going to talk about a solar system 40 light-years away that's bringing us closer than ever to answering the biggest question in science. 7 Earth-sized planets packed so close together you could fit the entire system inside the orbit of Mercury. 3 of them sitting in the habitable zone where liquid water could exist. And 1 planet in particular might just be our best shot at finding another habitable world. The James Webb Space Telescope has turned its instruments toward this system, and what it's finding is extraordinary. For the first time, we're getting real data about whether an Earth-sized planet in the habitable zone actually has an atmosphere. And by the end of tonight, you're going to understand exactly what Webb has discovered, why the tentative signs of a methane atmosphere have scientists so excited, and what this means for the search for life beyond Earth. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. In 2015, astronomers using a telescope in Chile made a discovery that would change everything. They found a star. Not just any star. A dim red dwarf about 40 light-years away in the constellation Aquarius. They called it TRAPPIST-1, named after the telescope that found it, TRAPPIST-South, the Transiting Planets and Planetesimals Small Telescope. It's barely bigger than Jupiter, with only about 9% the mass of our Sun. Its surface temperature hovers around 4,600 degrees Fahrenheit, which sounds hot until you realize our Sun burns at about 10,000 degrees Fahrenheit. This star is so small and cool that if you replaced our Sun with TRAPPIST-1, the entire star would comfortably fit between Mercury and the Sun. In May 2016, the team announced they'd found 3 planets orbiting this tiny star. All of them roughly Earth-sized, all of them transiting across the star's face from our perspective, creating tiny dips in the star's brightness that revealed their existence. The discovery made waves in the astronomical community. 3 Earth-sized planets around a single nearby star was already remarkable. But the TRAPPIST team suspected there might be more. The transit timing variations, the slight irregularities in when the planets crossed the star's face, suggested additional gravitational influences. Hidden planets tugging on the ones they could see. This is where NASA's Spitzer Space Telescope entered the story. Spitzer was an infrared observatory that had been launched back in 2003. By 2016, it had outlived its primary mission and was operating on an extended mission, running out of coolant, but still functional and still making incredible discoveries. The TRAPPIST team requested time on Spitzer for an unusual observation. They wanted to watch TRAPPIST-1 continuously for 21 days straight. This was a huge ask. 21 days of uninterrupted observations on a single target. Most Spitzer programs got a few hours here and there, not weeks of continuous coverage. But the potential payoff was enormous. If there really were multiple planets around TRAPPIST-1, continuous monitoring would catch every single transit. NASA approved the request. In September 2016, Spitzer locked onto TRAPPIST-1 and didn't look away for 3 weeks. Every few seconds, it measured the star's brightness with extraordinary precision, watching for those characteristic dips that signal a planet passing in front of the star. What emerged from that data was extraordinary. Not 3 planets, 7. 7 distinct transit signals, each with its own period, its own depth, its own characteristics. TRAPPIST-1 wasn't just a planetary system. It was a packed planetary system, with more Earth-sized worlds than any other known star. The announcement came in February 2017, and it made headlines worldwide. This wasn't just another exoplanet discovery. This was a complete planetary system, and 3 of those planets, maybe 4, sat squarely in the habitable zone, the region where temperatures allow liquid water to exist on a planet's surface if conditions are right. To understand how remarkable this is, you need to grasp the scale we're talking about. The innermost planet, TRAPPIST-1b, orbits just 1.1 million miles from its star. That's closer than any planet in our solar system gets to the Sun. Mercury, our innermost planet, orbits at 36 million miles. The outermost TRAPPIST-1 planet, designated H, orbits at about 5.8 million miles. The entire 7-planet system occupies a region just 4.7 million miles across. For comparison, Venus, the closest planet to Earth, comes within 38 million miles of us at its nearest approach. The TRAPPIST-1 planets are more tightly packed than anything in our solar system. You could fit all 7 planets and their orbits inside the orbit of Mercury with room to spare. In fact, you could fit the entire TRAPPIST-1 system inside Mercury's orbit at least 4 times. But here's the thing that makes this possible. TRAPPIST-1 is incredibly dim. It produces only a tiny fraction of the light our Sun does. This means the habitable zone, the region where water can be liquid, exists much closer to the star. If these planets were orbiting a Sun-like star at these distances, they'd be instantly vaporized. Around TRAPPIST-1, they're in the sweet spot. The planets themselves are fascinating. Transit timing variations, the subtle gravitational tugs the planets exert on each other, allowed astronomers to calculate their masses with remarkable precision. Combined with their sizes measured from transits, this gave us their densities. And the densities told a clear story. These are rocky worlds. All 7 of them. Not gas giants like Jupiter, not ice giants like Neptune, but terrestrial planets with solid surfaces. TRAPPIST-1b, the innermost, has a radius of about 1.09 times Earth's and a mass of 1.37 times Earth's. TRAPPIST-1c, the second planet, is slightly smaller, 0.91 times Earth's radius. Then comes TRAPPIST-1d at 0.77 Earth radii. TRAPPIST-1e, the fourth planet, and the one we're most interested in, has a radius of 0.92 times Earth's and a mass of 0.69 times Earth's. TRAPPIST-1f is slightly larger than Earth at 1.04 Earth radii. TRAPPIST-1g is 1.13 Earth radii. And the outermost, H, comes in at about 0.75 Earth radii, though its properties are less well constrained. But here's what made astronomers really excited. The densities suggested these planets aren't just rocky, they're different from Earth in composition. About 8% less dense than they would be if they had Earth's makeup. This likely means they contain more water. Not oceans on the surface necessarily, but water locked in their structures, perhaps as ice deep underground or water vapor in their atmospheres. A 2018 study suggested that some TRAPPIST-1 planets could harbor far more water than Earth's oceans. The planets closest to the star might have atmospheric water vapor. The middle planets could have liquid water oceans. The outer planets might be frozen ice worlds. All 7 planets complete their orbits remarkably quickly. TRAPPIST-1b takes just 1.51 days to orbit its star. TRAPPIST-1e, our main focus tonight, completes an orbit in 6.1 days. Even the outermost planet, TRAPPIST-1h, orbits in just 18.8 days. For comparison, Mercury takes 88 days to orbit our Sun. These are fast orbits because the planets are so close to their star. And that closeness creates another fascinating feature. The planets are almost certainly tidally locked. This means the same side of each planet always faces the star, just like how the same side of our Moon always faces Earth. One hemisphere would be in permanent daylight, the other in permanent night. The day side would be scorching hot, the night side frozen. But here's where atmospheres become crucial. An atmosphere could redistribute heat from the day side to the night side, making both hemispheres potentially habitable. Without an atmosphere, tidal locking would make these planets far less hospitable to life. The star itself, TRAPPIST-1, is estimated to be around 7.6 billion years old. That's older than our solar system, which formed about 4.6 billion years ago. This means the TRAPPIST-1 planets have had plenty of time for life to evolve if conditions were right. But there's a serious problem. Red dwarf stars, especially young ones, are violent. They produce intense flares, bursts of high-energy radiation that can strip away planetary atmospheres. TRAPPIST-1 is particularly active. It experiences regular flare events, some powerful enough to be detected from Earth 40 light-years away. These flares blast the inner planets with X-rays and ultraviolet radiation. Over billions of years, this radiation could have stripped away any atmospheres the planets once had, leaving them as barren rocks. This is the fundamental question that drives the search for atmospheres on TRAPPIST-1 planets. Have they managed to hold on to their atmospheres despite the radiation? Or did they lose them long ago? Among the 7 TRAPPIST-1 planets, 3 stand out as potentially habitable. TRAPPIST-1d, E, and F all orbit within or near the habitable zone. Some models include TRAPPIST-1g as well, though it's likely too cold. But TRAPPIST-1e quickly became the prime target for detailed study. Why? Several factors made it stand out. First, its position. It sits right in the middle of the habitable zone, not on the inner edge where it might be too hot, not on the outer edge where it might be too cold, but right in the sweet spot. Scientists call this the optimistic habitable zone, the region where liquid water is most likely to exist on a planet's surface given reasonable atmospheric compositions. TRAPPIST-1d sits on the inner edge of this zone. It receives more stellar flux, making it warmer. If it has a thick atmosphere with significant greenhouse warming, it could end up too hot, like a mini Venus. TRAPPIST-1f sits in the habitable zone too, but farther out, it's cooler, receiving less stellar flux. It would need a thicker atmosphere with more greenhouse gases to maintain liquid water. TRAPPIST-1e is in between, just right. It receives about 60% of the stellar flux that Earth gets from the Sun. That's more than Mars receives. About 43%, but less than Earth. With the right atmosphere providing greenhouse warming, TRAPPIST-1e could maintain liquid water on its surface, without getting too hot or too cold. Second, the planet's properties. Its equilibrium temperature, the temperature it would have with no atmosphere, ranges from -48 degrees Fahrenheit to -16 degrees Fahrenheit, depending on how reflective its surface is. Cold, but not impossibly so. An atmosphere with greenhouse gases like carbon dioxide or methane could warm the surface significantly. The planet's size and mass make it eerily similar to Earth. With 0.92 Earth radii and 0.69 Earth masses, It's only slightly smaller and less massive than our homeworld. Its surface gravity is about 82% of Earth's. If you weigh 150 pounds on Earth, you'd weigh 123 pounds on TRAPPIST-1e. Not a huge difference. A 2021 study analyzing the planet's density suggested something intriguing. If iron makes up 25% or more of the planet's total mass, similar to Earth, then TRAPPIST-1e must have a higher water mass fraction than Earth to account for its lower density. This could mean vast amounts of water, either as ice, liquid oceans, or atmospheric vapor. A November 2018 analysis determined that of all 7 TRAPPIST-1 planets, TRAPPIST-1e has the best chance of being an Earth-like ocean planet, the one most worthy of further study regarding habitability. The Habitable Exoplanets Catalog, maintained by the University of Puerto Rico at Arecibo, lists TRAPPIST-1e among the best potentially habitable exoplanets discovered. But there's a catch. All of this depends on one critical factor. Does TRAPPIST-1e have an atmosphere? Without an atmosphere, the planet is just a frozen rock. With an atmosphere, it could be a water world, potentially capable of supporting life. This is where previous observations fell short. NASA's Hubble Space Telescope observed TRAPPIST-1e and other planets in the system. Hubble ruled out thick, hydrogen-rich atmospheres like those on Neptune. Those observations were important, but they couldn't detect the kinds of atmospheres we're really interested in. Atmospheres like Earth's, dominated by nitrogen and oxygen. Or atmospheres like Venus's, thick with carbon dioxide. Or even atmospheres like Titan's, Saturn's moon, with nitrogen and methane. Hubble simply wasn't sensitive enough to detect these high mean molecular weight atmospheres on such small planets so far away. Spitzer provided valuable data about the planet's sizes, masses, and densities, but it too lacked the sensitivity to characterize their atmospheres in detail. By 2021, the scientific community was clear about what needed to happen next. TRAPPIST-1e required observation by the most powerful space telescope ever built, the James Webb Space Telescope. On December 25, 2021, the James Webb Space Telescope launched from French Guiana. It was a moment astronomers had been waiting for more than 2 decades. Webb is not just an upgrade to Hubble. It's a completely different class of observatory. Its primary mirror measures 6.5 meters across, or 21 feet, composed of 18 gold-coated beryllium hexagons. It collects more than 6 times as much light as Hubble's mirror. But the real game-changer is Webb's infrared capability. While Hubble primarily observes in visible and ultraviolet light, Webb is optimized for infrared. This is crucial for studying exoplanet atmospheres. When a planet transits in front of its star, some of the star's light passes through the planet's atmosphere before reaching us. Different molecules in that atmosphere absorb specific wavelengths of light. Water vapor absorbs certain infrared wavelengths. Carbon dioxide absorbs others. Methane has its own spectral fingerprint. By measuring which wavelengths are absorbed during a transit, astronomers can determine what molecules are present in the planet's atmosphere. This technique is called transmission spectroscopy. Webb's near-infrared spectrograph, or NIRSpec, is specifically designed for this. It can split incoming light into its component wavelengths with extraordinary precision, creating a spectrum that reveals the chemical composition of whatever it's observing. For exoplanet atmospheres, this is revolutionary. Webb also has another advantage: its position. The telescope orbits the Sun at a location called the second Lagrange point, or L2, about 1 million miles from Earth. At L2, Webb can continuously observe a target without interruption from Earth or the Moon passing through its field of view. This stability is essential for detecting the tiny signals from exoplanet atmospheres. The journey to L2 took about a month after launch. During that time, Webb executed one of the most complex deployment sequences ever attempted in space. The telescope was too large to fit in any rocket fully assembled. It had to be folded up like origami, then carefully unfold itself in the vacuum of space. First, the sun shield deployed. This is a 5-layer structure, the size of a tennis court, each layer thinner than a human hair. The sun shield keeps Webb's instruments cold, minus 390 degrees Fahrenheit. This extreme cold is necessary for infrared astronomy. If the telescope were warm, it would emit its own infrared radiation, drowning out the faint signals from distant objects. Then, the mirror segments unfolded. 18 hexagonal pieces of gold-coated beryllium, each weighing about 46 pounds. They unfolded from their stowed positions and locked into place, forming that 6.5-meter primary mirror. But they weren't aligned yet. Each segment had to be adjusted, tilted, and moved by microscopic amounts, using tiny motors on the back of each mirror. The alignment process took months. Astronomers pointed Webb at a bright star and measured how light from that star hit each mirror segment. Then, they adjusted the segments, repeating the process hundreds of times until all 18 segments acted as one perfect mirror. The precision required was extraordinary. The segments had to be aligned to within 50 nanometers. That's 50 billionths of a meter, about 1,000th the width of a human hair. About 1,000th the width of a human hair. If the Webb mirror was scaled up to the size of the United States, the allowable error would be about 1.5 inches. And this alignment had to be maintained in space, where temperature changes, micrometeorite impacts, and the thermal stresses of moving between sunlight and shadow constantly try to push things out of alignment. Webb has a system called wavefront sensing that continuously monitors the mirror alignment and makes tiny adjustments to keep it perfect. All of this engineering, all of this complexity, was necessary to create a telescope powerful enough to study exoplanet atmospheres, to detect the minuscule absorption features from molecules in the thin shells of gas surrounding distant rocky worlds. The instruments aboard Webb are equally sophisticated. NIRSpec, the near-infrared spectrograph, is the primary tool for exoplanet atmosphere studies. It can observe light from 0.6 to 5.3 microns. That's infrared light, longer wavelengths than visible light. This range is crucial because many important molecules absorb strongly in the infrared. Water vapor has absorption features at 1.4 and 1.9 microns. Carbon dioxide absorbs at 1.6, 2.0, 2.7, and 4.3 microns. Methane absorbs at 1.7, 2.3, and 3.3 microns. By splitting incoming light into a spectrum and measuring the intensity at each wavelength, NIRSpec can identify which molecules are present. But there's a challenge. The signals are incredibly faint. When TRAPPIST-1 transits its star, the planet blocks about 0.7% of the star's light. That's the signal from the planet itself, the total amount of light blocked. The atmospheric signal, the additional absorption from molecules in the atmosphere is much smaller. Maybe 0.005%. A tiny fraction of an already small signal. To detect this, NIRSpec has to be extraordinarily sensitive. It uses state-of-the-art infrared detectors that can count individual photons. And it has to collect light for hours during each transit to build up enough signal to measure those absorption features. Even then, the data is noisy. Statistical fluctuations, cosmic rays hitting the detector, slight changes in the telescope's pointing, thermal variations affecting the instrument. All of these create noise that can mask the signal. This is why multiple observations are necessary. Each transit observation adds more data. The signal builds up, while the noise, being random, averages out. With enough observations, the real signal emerges from the noise. This is the process that's currently underway with TRAPPIST-1e. 4 transits observed so far, 15 more in progress. Each one adding to the dataset, making the eventual answer clearer. But there's a unique challenge with TRAPPIST-1. The star itself is the problem. TRAPPIST-1 is an M-dwarf, cool enough that its own atmosphere contains molecules. Our Sun is too hot for molecules to exist in its outer layers. The gases are ionized, broken apart into individual atoms. But TRAPPIST-1, with a surface temperature of only 4,600 degrees Fahrenheit, is cool enough for molecules to form and survive. Water, carbon monoxide, methane, and other molecules exist in TRAPPIST-1's atmosphere. When we observe a planet transiting TRAPPIST-1, the starlight passing through the planet's atmosphere has already passed through the star's atmosphere. The star's atmosphere has its own spectral features. Water absorption from the star, carbon monoxide from the star. These features appear in the spectrum, mixed in with any features from the planet's atmosphere. This creates what astronomers call stellar contamination. Features in the spectrum that might look like they're from the planet's atmosphere could actually be from the star. Separating the two is extremely difficult. It requires detailed models of the star's atmosphere, careful observations of the star when no planet is transiting to measure the baseline spectrum, and sophisticated statistical analysis to determine what's planet and what's star. There's another complication. TRAPPIST-1's surface is not uniform. Like our Sun, it has dark regions called star spots and bright regions called faculae. Star spots are cooler areas where magnetic fields suppress convection. They're like supersized versions of sunspots. Faculae are hotter, brighter regions. As TRAPPIST-1 rotates, these features move across the visible disk of the star. The star's brightness changes slightly as darker spots rotate into view or rotate out. This is called rotational modulation. TRAPPIST-1 rotates once every 3.3 days, so the star's brightness varies on that timescale. But it's worse than that. The spots and faculae aren't static. They evolve, growing and shrinking and changing on timescales of days to weeks. This means the star's spectrum changes over time, not just from rotation, but from real changes in the surface features. When a planet transits across TRAPPIST-1, it might pass in front of a star spot. The spot is cooler than the surrounding surface, so when the planet blocks it, the average temperature of the visible surface increases slightly. This changes the spectrum, or the planet might pass in front of a facula. Then the average temperature decreases. Again, the spectrum changes. These effects can mimic atmospheric absorption features. They can create false signals that look like molecules in the planet's atmosphere, but are actually just artifacts of the star's surface features. TRAPPIST-1 is particularly problematic in this regard. It's an active star with prominent star spots and faculae. Observations of other TRAPPIST-1 planets have shown clear evidence of stellar contamination. The same features appearing in spectra from different planets, which must mean they're from the star, not the planets. This is the challenge Webb faces with TRAPPIST-1, detecting a real atmospheric signal amid all this stellar noise. It's like trying to hear a whisper in a loud room. The whisper is there, but you have to filter out all the background noise to hear it. That's what the next round of observations is attempting to do. By observing both TRAPPIST-1e and TRAPPIST-1b in close succession, astronomers can measure the stellar contamination from B's transit. TRAPPIST-1b is almost certainly airless, so any spectral features in its transit must be from the star. Those same features should appear in TRAPPIST-1e's spectrum. By subtracting them out, what remains should be the true atmospheric signal from TRAPPIST-1e, if there is one. This differential measurement technique is one of the cleverest approaches devised for dealing with stellar contamination. It's not perfect. The two planets might pass across slightly different parts of the star's surface, encountering different star spots. But it's better than trying to model the stellar contamination from first principles. It uses real data to measure the contamination, then removes it. This is cutting-edge science. Techniques being developed and refined in real time as the observations progress. 5 years ago, astronomers weren't sure this would work. Now they're doing it. Observing Earth-sized planets 40 light-years away, dealing with stellar contamination, extracting atmospheric signals from noisy data. It's extraordinary. And it's happening right now. But if any telescope could do it, Webb could. By mid-2022, Webb completed its commissioning phase and began full science operations. TRAPPIST-1 was a priority target. The telescope's scientific team, working under a program called DREAMS, Deep Reconnaissance of Exoplanet Atmospheres using multi-instrument spectroscopy, devoted over 400 hours of observation time to the TRAPPIST-1 system. That's an enormous allocation. It reflects how important this system is to the search for habitable worlds. The observations began with the innermost planets. TRAPPIST-1b and c were observed first. These planets are too hot to be habitable, but studying them would help astronomers understand the stellar contamination problem and refine their techniques before tackling the habitable zone planets. Results for TRAPPIST-1b came in March 2023. Webb's MIRI instrument, the mid-infrared instrument, measured the planet's dayside temperature at about 450 degrees Fahrenheit. Hot, as expected for a planet that close to its star. More importantly, the observations found little evidence of an atmosphere. TRAPPIST-1b appeared to be a bare rock. Its lack of atmosphere made sense. Being the innermost planet, it receives the most intense radiation from the star. Any atmosphere it once had was likely stripped away billions of years ago. Results for TRAPPIST-1c were more ambiguous. If it has an atmosphere, it's very thin. It might be a bare rock like B, or it might have a tenuous atmosphere that's difficult to detect. Then came TRAPPIST-1d. This planet sits on the inner edge of the habitable zone. It's slightly cooler than C, so it had a better chance of retaining an atmosphere. But when the results came in, they were disappointing. No clear signs of an atmosphere. No detection of water, vapor, methane, or carbon dioxide. The data ruled out thick, Earth-like atmospheres dominated by nitrogen and oxygen. It also ruled out thick carbon dioxide atmospheres like Venus or Mars. TRAPPIST-1d might have a very thin atmosphere, but more likely it's another airless world. 3 planets down. 3 strikes. This was starting to look like a pattern. The TRAPPIST-1 planets, bombarded by stellar radiation for billions of years, might have all lost their atmospheres. But there were still 4 planets left to study. And the next one was TRAPPIST-1e, the planet right in the middle of the habitable zone, the one with the best chance of being truly Earth-like. Between late 2023 and early 2025, Webb observed TRAPPIST-1e during 4 separate transits. Each observation used near-spec in its prism mode, which provides broad wavelength coverage from 0.6 to 5.3 microns. That's infrared light, invisible to human eyes, but perfect for detecting molecular absorption. Each transit observation required hours of continuous monitoring. Webb had to capture the star's spectrum before the planet began its transit. During the transit, as the planet blocked part of the star's light, and after the transit, when the planet moved away. By comparing the spectrum during the transit to the spectrum before and after, astronomers could isolate the tiny signal from the planet's atmosphere, if it has one. The data analysis took months. This isn't like taking a photograph where you immediately see the result. The raw data from Webb required careful calibration, removing instrumental effects, accounting for cosmic ray hits on the detector, and dealing with the star's own variability. The team, led by Nestor Espinosa at the Space Telescope Science Institute and Anna Glidden at MIT, worked through every possible source of error. In September 2025, they published their initial results in the Astrophysical Journal Letters. 2 papers, both presenting the same data but exploring different atmospheric scenarios. What did they find? The results were intriguing. The spectrum showed features. Small absorption dips at certain wavelengths that could tell us whether this planet has air. The observations immediately ruled out several scenarios. Thick, hydrogen-rich atmospheres, definitively ruled out. The data showed no evidence for the strong spectral features hydrogen would produce. This was good news, because primordial hydrogen atmospheres aren't conducive to life as we know it. Thick carbon dioxide atmospheres like Venus or Mars, also ruled out. Carbon dioxide has very strong absorption features in the wavelength range, Webb observed. If TRAPPIST-1e had a thick carbon dioxide atmosphere, Webb would have seen it clearly. It didn't. So, what possibilities remain? This is where it gets exciting. The data allows for 2 main scenarios. First, TRAPPIST-1e could be a bare rock with no significant atmosphere. The small features in the spectrum could be entirely due to stellar contamination. The star's own atmosphere, combined with star spots and bright faculae, could produce signals that mimic a planetary atmosphere. This would be consistent with what Webb found for TRAPPIST-1b, C, and D. All of them appear to have lost their atmospheres. But there's a second possibility, and this one has scientists excited. TRAPPIST-1e could have a thin atmosphere dominated by nitrogen, similar to Earth. Nitrogen doesn't absorb strongly in the infrared, so it's essentially invisible to Webb. But the data showed something else. Hints of methane. Small absorption features at wavelengths where methane absorbs. If those features are real and not stellar contamination, they could indicate a nitrogen-dominated atmosphere with traces of methane, like a warm version of Saturn's moon Titan. The data shows a tentative preference for this scenario. It's not definitive. Scientists can't completely rule out the possibility that TRAPPIST-1e is a cold, barren, airless world with no atmosphere at all. But the methane hints are there. And if they're real, this could be exactly the kind of atmosphere that supports liquid water. Nestor Espinosa, one of the lead researchers, stated it clearly. Webb's infrared instruments are giving us more detail than we've ever had access to before. The initial 4 observations show us what we will have to work with when the rest of the information comes in. Anna Glidden's analysis emphasized the uncertainty. Based on 4 observations, TRAPPIST-1e is equally likely to have or not have an atmosphere. The data simply isn't sensitive enough yet to tell the difference. So, where does that leave us as of early 2026? The honest answer is that we're in an incredibly exciting position, but we don't yet know for certain which scenario is correct. The data points in an intriguing direction. TRAPPIST-1e might have an atmosphere. Not the thick hydrogen envelope we've ruled out. Not the carbon dioxide blanket, like Venus, that we've also ruled out. But possibly a thin nitrogen atmosphere with methane. One that could support liquid water on at least part of the surface. But scientists can't completely rule out that TRAPPIST-1e is a bare rock with no atmosphere at all. Here's what we know with confidence. TRAPPIST-1e doesn't have a thick, puffy hydrogen atmosphere. Those were ruled out years ago by Hubble. It doesn't have a thick carbon dioxide atmosphere like Venus. Webb's data definitively rules that out. Mars-like atmospheres are also unlikely. If carbon dioxide were present in significant amounts, even in a thin atmosphere, Webb should have detected it. Could the planet have a nitrogen-oxygen atmosphere like Earth's? That's consistent with the observations. Nitrogen and oxygen don't have strong infrared absorption features, so Webb can't detect them directly. But if it's Earth-like, we'd expect to see water vapor and carbon dioxide as well. Their absence is puzzling. This is why the methane hints are so intriguing. Methane is a powerful greenhouse gas. If TRAPPIST-1e has a nitrogen atmosphere with several percent methane, that methane could provide enough warming to allow liquid water. The planet could have liquid water on its star-facing side, creating what scientists call terminator habitability. A band of habitable conditions in the perpetual twilight zone between eternal day and eternal night. Or it could even have a global ocean beneath a thick, hazy atmosphere. An alien world, orange and hazy like Titan, but with liquid water instead of liquid methane. These possibilities are extraordinary. But the methane signatures could also be stellar contamination. And that's the challenge we're facing right now. In December 2025, a third paper appeared that raised important questions. Sukrit Ranjan at the University of Arizona and his colleagues asked, if TRAPPIST-1e really has a methane atmosphere, where is that methane coming from? This is a critical question because of photochemistry. When ultraviolet light from a star hits a planet's atmosphere, it drives chemical reactions that can destroy molecules. Titan, Saturn's moon, has a methane-rich atmosphere, but Titan is very cold. Its surface temperature is minus 290 degrees Fahrenheit. At those temperatures, chemical reactions happen very slowly. Methane can persist for millions of years. TRAPPIST-1e is much warmer. Even in the habitable zone, it would be above freezing. At warmer temperatures, photochemistry works much faster. Ranjan's team calculated that methane should be destroyed on timescales of tens of thousands to millions of years. That sounds like a long time, but geologically, it's instantaneous. For methane to persist, there must be a source constantly replenishing it. On Earth, that source is primarily biology. Methanogenic bacteria produce vast amounts of methane. There are also non-biological sources. Volcanic activity and serpentinization reactions between water and rocks can produce methane. But on Earth, biological sources produce over 1,000 times more methane than geological ones. For TRAPPIST-1 to maintain methane in its atmosphere, it needs either intense geological activity far beyond anything on Earth or biology. This is why the methane hints are so exciting. If confirmed, they could point to life. But Ranjan's paper also raises another possibility. The methane might not be from the planet at all. It could be from the star. TRAPPIST-1 is cool enough that methane exists in its own atmosphere. When we observe a planet transit, we're seeing starlight that passed through the star's atmosphere. Methane in the star could create absorption features that look identical to methane in the planet's atmosphere. This is called stellar contamination, and it's a serious challenge. With only 4 observations, it's impossible to separate planet from star with certainty. The methane hints could be real atmospheric features pointing to geology or even biology. Or they could be interference from the host star. This is why the ongoing observations are so critical. While astronomers were working on TRAPPIST-1, Webb continued observing the other planets in the system. By early 2026, over 400 hours of Webb observations have been devoted to the TRAPPIST-1 system. That's an enormous investment. It reflects just how important this system is. As of May 2026, the scientific community has reported on 4 of the 7 planets, B, C, D, and E. TRAPPIST-1b, the innermost planet, appears to be a bare rock with no atmosphere. Its dayside temperature matches what we'd expect for an airless world absorbing starlight. No greenhouse effect, no atmospheric heat redistribution. Just a hot rock baking under the star's rays. TRAPPIST-1c is more uncertain. If it has an atmosphere, it's very thin and difficult to detect. Most likely, it's another bare rock, but the data aren't conclusive. TRAPPIST-1d, on the inner edge of the habitable zone, shows no signs of an Earth-like atmosphere. No thick carbon dioxide atmosphere, like Venus or Mars either. It might have a very tenuous atmosphere, or it might be airless. Either way, it's not looking like a habitable world. TRAPPIST-1 is the ambiguous case we've been discussing. Maybe atmosphere, maybe not. Data analysis ongoing. That leaves 3 planets, F, G, and H. TRAPPIST-1 F orbits in the habitable zone, slightly farther from the star than E. It receives less stellar flux, making it cooler. It's also slightly larger than Earth, with 1.04 Earth radii and 1.04 Earth masses. A true Earth twin in size. TRAPPIST-1g is another habitable zone candidate, though on the outer edge. It's even larger, with 1.13 Earth radii and 1.32 Earth masses. A super-Earth. TRAPPIST-1 H is the outermost planet, likely too cold to be habitable unless it has a very thick atmosphere with extreme greenhouse warming. Observations of F, G, and H are ongoing. Initial results were expected through 2026. The pattern emerging from B, C, D, and E is concerning. So far, we haven't found any clear evidence of atmospheres on the TRAPPIST-1 planets. The innermost planets definitely don't have them. TRAPPIST-1e might, but it's unclear. This raises a troubling question. Do any of the TRAPPIST-1 planets have atmospheres? Or did they all lose them to stellar radiation? Red dwarf stars, especially ultra-cool M dwarfs like TRAPPIST-1, have a difficult relationship with planetary atmospheres. When these stars are young, they're incredibly active. They produce constant flares and emit intense X-ray and ultraviolet radiation. This high-energy radiation can split water molecules in a planet's atmosphere into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen can either escape as well or react with surface rocks. Over millions of years, this process can strip away enormous amounts of water. Models suggest that the inner TRAPPIST-1 planets, B and C, could have lost multiple Earth oceans worth of water this way. TRAPPIST-1 is now 7.6 billion years old. It's past its most violent youth. But for billions of years, it was blasting its planets with radiation. The question is whether planets at Earth-like distances in the habitable zone could have survived that onslaught. Some models say yes. If a planet started with a thick enough atmosphere or had volcanic activity continuously replenishing lost gases, it could maintain an atmosphere. Other models say no. The radiation is too intense, too prolonged. Even habitable zone planets would be stripped bare. The TRAPPIST-1 observations are testing these models. If we find that E, F, and G have atmospheres, it suggests planets around red dwarfs can hold onto their air. If we find they're all airless, it suggests atmospheres are extremely difficult to maintain around these stars. This matters far beyond one system. Red dwarf stars make up about 75% of all stars in our galaxy. There are hundreds of billions of them in the Milky Way alone. And because red dwarfs are small, their habitable zones are close in. This means planets in habitable zones around red dwarfs transit more frequently and produce stronger atmospheric signals than planets around sun-like stars. They're easier to study. If red dwarf planets can have atmospheres and be habitable, then the galaxy could be teeming with habitable worlds. If they can't, if stellar radiation always strips their atmospheres, then habitable planets are much rarer. This is one of the most important questions in astrobiology. And TRAPPIST-1 is our best laboratory for answering it. Beyond the immediate question of atmospheres, there's an even more profound goal: the search for biosignatures. Signs of life. If TRAPPIST-1e has an atmosphere, the next step is determining whether that atmosphere shows evidence of biological activity. On Earth, life has transformed our atmosphere in dramatic ways. Before life emerged, Earth's atmosphere was mostly nitrogen and carbon dioxide with trace methane from volcanic sources. Then, photosynthetic bacteria evolved. They began using sunlight to convert carbon dioxide and water into organic compounds and oxygen. Over billions of years, oxygen built up in the atmosphere. Today, our atmosphere is 21% oxygen. That oxygen is a biosignature. It's produced by life and consumed by geology. Without constant replenishment from photosynthesis, oxygen would disappear from our atmosphere in just a few million years. The presence of abundant oxygen is a sign of ongoing biological activity. But there's a problem with oxygen as a biosignature. Oxygen is produced through photosynthesis, which evolved on Earth about 2.4 billion years ago. Before that, Earth had life, but the atmosphere contained almost no oxygen. Those early organisms were anaerobic. They didn't produce oxygen. If we were observing Earth 3 billion years ago from 40 light years away, we wouldn't see oxygen. We'd miss the life that was there. This led astrobiologists to propose alternative biosignatures. One of the most promising is the methane-carbon dioxide disequilibrium pair. Here's the idea. Methane and carbon dioxide together are thermodynamically unstable. They want to react with each other, forming water and organic compounds. In a planetary atmosphere, methane should be destroyed by ultraviolet light and oxidized by any available oxygen or carbon dioxide. For methane to coexist with carbon dioxide in an atmosphere, there must be a constant source of methane. On Earth, that source is biology. Methanogenic bacteria produce vast amounts of methane. They exist in swamps, wetlands, ocean sediments, and the guts of animals. Without life, Earth's atmosphere would have almost no methane. The coexistence of methane and carbon dioxide, especially if the methane is present in large amounts, is difficult to explain without biology. This is why the tentative methane hints in TRAPPIST-1's spectrum were so exciting. If confirmed, methane at the levels suggested, several percent, would be very difficult to explain through non-biological processes. Volcanic activity can produce some methane, but not in those quantities. Serpentinization, the reaction between water and certain rocks, can produce methane, but again, not at percent levels. Getting to several percent methane requires either extreme geological activity beyond anything we see in our solar system or biology. But as we discussed, the methane detection is uncertain. It could be stellar contamination. Even if it's real, Ranjan's photochemistry paper showed that methane shouldn't be stable in a warm atmosphere, unless there's a very strong source, like life. This is the tantalizing possibility. If future observations confirm the methane and rule out stellar contamination, TRAPPIST-1 could be showing us a biosignature. Not a definitive proof of life, but a strong hint. Strong enough to justify decades of follow-up observations. The detection of biosignatures on an exoplanet would be one of the most important discoveries in human history. It would mean we're not alone. That life exists elsewhere in the universe. That Earth is not unique. This is what drives the TRAPPIST-1 observations. Not just curiosity about distant planets, but the profound question of whether life exists beyond our world. What makes the TRAPPIST-1 observations truly revolutionary isn't just what they might find, but what they represent. For the first time in history, we're characterizing the atmospheres of Earth-sized planets around another star. Think about how remarkable that is. TRAPPIST-1 is 235 trillion miles away. That's the distance light travels in 40 years. The planet itself is barely larger than Earth. And we're attempting to detect and measure its atmosphere, a thin shell of gas just tens of miles thick. The technical achievement required to do this is staggering. When TRAPPIST-1 transits its star, it blocks about 0.7% of the star's light. That's the signal from the planet itself. The atmospheric signal is far smaller, maybe 0.005%. A tiny fraction of a tiny fraction. Webb has to detect that minuscule signal from 40 light-years away, separate it from the star's own spectrum, account for stellar contamination from star spots and faculae, and extract meaningful information about the planet's atmospheric composition. It's like trying to analyze the composition of a candle's flame from 1,000 miles away while someone is waving the candle around and shining a searchlight next to it. The fact that we can do this at all is astounding. 10 years ago, astronomers weren't sure it would be possible. The technology didn't exist. Now, with Webb, we're actually doing it. And we're learning things. Even the non-detections are informative. The fact that TRAPPIST-1b, C, and D appear to lack atmospheres tells us something important about how red dwarf stars affect their planets. The ambiguous results for TRAPPIST-1e tell us we're at the edge of what current technology can achieve. We need more data, better techniques, possibly even next-generation telescopes to answer the question definitively. But we're in the game. We're observing Earth-sized planets in the habitable zones of nearby stars and attempting to determine whether they could support life. This is what exoplanet science has been building toward for 3 decades. Since the first exoplanet discoveries in the 1990s, astronomers have progressed from simply detecting planets to measuring their sizes and masses to now characterizing their atmospheres. TRAPPIST-1e represents the cutting edge of this progression, an Earth-sized world in the habitable zone where we're searching for signs of air and water and possibly even life. The story of TRAPPIST-1e is far from over. In fact, it's just beginning. Remember those 4 transit observations that produced the ambiguous results? They were just the start. There are 15 more Webb observations of TRAPPIST-1e scheduled. By late 2025, Nestor Espinosa said they were halfway through. The observations should be done by December 2025. Results will be published through 2026. These additional observations use a clever technique to reduce stellar contamination. Webb is observing both TRAPPIST-1e and TRAPPIST-1b during closely spaced transits. The 2 planets trace nearly the same track across the star's disk. TRAPPIST-1b appears to be a bare rock with no atmosphere. Any spectral features in TRAPPIST-1b's transit spectrum must be from the star, not from the planet. By comparing the spectra from TRAPPIST-1b and TRAPPIST-1e, astronomers can identify which features are stellar contamination and which might be real atmospheric signals from TRAPPIST-1e. It's a differential measurement. Subtract out the stellar contribution, and what remains should be the planetary atmosphere, if there is one. This technique should significantly improve the sensitivity of the observations. It might be enough to definitively answer whether TRAPPIST-1e has an atmosphere, and if it does, what kind of atmosphere it is. The scheduling of these observations is complex. TRAPPIST-1e transits its star every 6.1 days. TRAPPIST-1b transits every 1.5 days. Finding times when both planets transit close together, within hours or days of each other, and when Webb can observe without interruption, requires careful planning months in advance. The observations are also competing for time on Webb. The telescope is the most oversubscribed observatory in history. Astronomers around the world want to use it for their projects. Every hour of observing time is precious. Getting 19 transits of TRAPPIST-1e approved represents an enormous vote of confidence in the importance of this target. It's a recognition that this is one of the most important questions we can answer. Does an Earth-sized planet in the habitable zone of a nearby star have an atmosphere? Results from these observations are expected through 2026. By the time you're watching this, some of those results might already be published. The next few months could bring major news. A definitive detection of an atmosphere, or a definitive conclusion that there is no atmosphere. Either answer would be profound. Beyond TRAPPIST-1e, Webb is continuing to observe the outer planets. TRAPPIST-1, F and G, both in or near the habitable zone, are under observation. These planets are farther from the star, so they receive less intense radiation. They might have had a better chance of retaining their atmospheres. But they're also cooler, which makes atmospheric features harder to detect. Webb's infrared instruments are less sensitive at the colder temperatures of the outer planets. The molecules freeze out, condensing into clouds or ice particles instead of remaining as gases in the atmosphere. Water vapor, for instance, might be present, but as ice crystals rather than gas. Ice doesn't produce the same absorption features as vapor. It scatters light instead of absorbing at specific wavelengths. This makes atmospheric characterization more challenging. Despite these difficulties, observations are ongoing. TRAPPIST-1F completes an orbit in 9.2 days. TRAPPIST-1G takes 12.4 days. Both have been observed multiple times by Webb. Data analysis is in progress. Results for F and G are expected through 2026 and 2027. There's also a new mission on the horizon. NASA's Pandora satellite is scheduled to launch in early 2026. If you're watching this after that launch, Pandora might already be in orbit and collecting data. Pandora is a small satellite, a small-sat mission, much smaller and less expensive than Webb. But it has a unique and crucial capability. Pandora is designed specifically to study exoplanet atmospheres around red dwarf stars and monitor stellar variability. Its unique capability is that it can monitor a star continuously before, during, and after a planetary transit. This allows it to track stellar variability, the changing brightness and spectrum as star spots rotate in and out of view. Red dwarfs, like TRAPPIST-1, have complex, active surfaces, star spots, and faculae, constantly evolving. Brightness, varying on hourly and daily timescales. By monitoring a star continuously for days or weeks, Pandora can build a detailed map of this variability. It can measure which parts of the star are spotted, how those spots evolve, and how they affect the spectrum. This information is crucial for separating stellar contamination from planetary atmospheric signals. With Pandora's stellar variability data combined with Webb's high-resolution spectra, astronomers can untangle the overlapping signals. They can say with confidence, this spectral feature is from the star, this one is from the planet. Pandora is led by Daniel Apai at the University of Arizona's Steward Observatory. The mission has been in development for several years, and TRAPPIST-1 is one of its primary targets. The satellite will monitor TRAPPIST-1 for extended periods, tracking every rotation, every flare, every change in brightness. This data will be invaluable for interpreting Webb's observations. The two missions are complementary. Webb provides the spectral resolution and sensitivity. Pandora provides the temporal coverage and stellar monitoring. Together, they form a powerful combination for studying exoplanet atmospheres around active red dwarf stars. Looking even further ahead, Webb's mission has been extended. When it launched, the nominal mission lifetime was 5.5 years. Based on fuel reserves needed to maintain its orbit and pointing, that would allow observing TRAPPIST-1 about 85 times during transits. But Webb has performed flawlessly. The launch was so precise that less fuel was needed for course corrections than expected. The telescope's operations have been efficient, using minimal fuel for pointing adjustments. Mission managers now estimate Webb could operate for 20 years, possibly longer. 20 years of observations. That would allow observing TRAPPIST-1 about 320 times, 320 transits. Imagine the dataset that would produce. With that much data, astronomers could detect extremely subtle atmospheric features, molecules present at parts per million concentrations. They could track seasonal changes if the planet has seasons. The orbital resonances between TRAPPIST-1 planets create complex gravitational interactions. These might drive atmospheric circulation patterns that vary over time. With 20 years of data, those patterns would be visible. Astronomers could search for extremely rare molecules that might be biosignatures. Phosphine, for instance, is produced by life on Earth, but destroyed rapidly by photochemistry. Its presence in an exoplanet atmosphere would be difficult to explain without biology. But phosphine absorbs at very specific wavelengths. Detecting it would require many observations to build up enough signal to noise. 20 years of Webb observations could find it if it's there. They could also build a comprehensive picture of the planet's climate and chemistry, how temperature varies across the surface, whether clouds form and dissipate, whether there's weather, seasonal cycles, long-term changes. 20 years is long enough to see evolution. If volcanic activity is releasing gases into the atmosphere, Webb could detect changes in composition over time. If biology is present and undergoes bloom cycles like algae on Earth, chemical signatures might vary seasonally. With enough data, these variations would be detectable. 20 years of observations would transform our understanding of TRAPPIST-1. From a mysterious world with ambiguous atmospheric hints to a fully characterized planet with known composition, climate, and possibly even signs of life. But 20 years is a long time. Most of us watching this won't wait 20 years for answers. We want to know now, or at least soon. The good news is that we don't need 20 years for preliminary answers. The current observation campaign, with 19 transits total, should be enough to detect an atmosphere, if it exists and has molecules like methane, carbon dioxide, or water vapor at detectable levels. We'll have those results within 1 or 2 years. By 2027 at the latest. That's soon. In the grand scheme of humanity's search for life beyond Earth, 2 years is nothing. We've been wondering about this question for thousands of years. We can wait 2 more. Beyond Webb and Pandora, astronomers are already planning next-generation telescopes. The Habitable Worlds Observatory, NASA's next flagship mission after Webb, is being designed specifically to search for biosignatures on exoplanets. It's still in the concept phase, with no firm design yet, but the goals are clear. A large space telescope, 6 to 8 meters in diameter, capable of direct imaging of exoplanets. Unlike Webb, which observes planets during transits when they pass in front of their stars, the Habitable Worlds Observatory will block out the star's light and directly image the planet. This allows studying the planet at any time, not just during transits. You can observe it continuously, watching how it changes over hours, days, and seasons. Direct imaging also allows studying planets that don't transit from our perspective. Most exoplanets don't transit. Their orbits are tilted such that they never pass in front of their star, as seen from Earth. With direct imaging, those planets become accessible. The Habitable Worlds Observatory will also have spectrographs capable of detailed atmospheric characterization, measuring the composition of directly imaged planets. Searching for biosignatures like oxygen and methane together, phosphine, dimethyl sulfide, and other gases that hint at biological activity. It won't launch until the 2040s at the earliest, probably closer to 2050. These flagship missions take decades to develop, build, and launch. But when it does launch, TRAPPIST-1e will be a prime target. If Webb has found hints of an atmosphere, the Habitable Worlds Observatory will study it in detail. The European Space Agency's Ariel mission, scheduled for launch in 2029, will conduct a systematic survey of exoplanet atmospheres. Unlike Webb, which observes a few targets in great detail, Ariel will observe hundreds of exoplanets, building a statistical understanding of atmospheric diversity. What kinds of planets have what kinds of atmospheres? Are rocky planets around red dwarfs typically airless, or do many of them have atmospheres? Do habitable zone planets have different atmospheric compositions than hot planets close to their stars? Are there patterns in atmospheric chemistry that tell us about planet formation and evolution? Ariel will answer these questions by surveying a large sample of exoplanets. TRAPPIST-1 planets will be included in that survey. The data will provide context for the detailed Webb observations. Is TRAPPIST-1e typical of habitable zone planets around red dwarfs, or is it unusual? Ground-based telescopes are also improving. The extremely large telescope, being built in Chile by the European Southern Observatory, will have a 39-meter mirror. That's enormous. Larger than any optical telescope ever built. It's so large that it can't be a single mirror. Instead, it's composed of 798 hexagonal segments, each 1.4 meters across, all working together as one giant mirror. When it begins operations in the early 2030s, the extremely large telescope will be capable of detailed atmospheric studies of nearby exoplanets. It will use adaptive optics to cancel out atmospheric turbulence, achieving resolution close to the theoretical limit set by the mirror size. And it will have spectrographs covering a wide wavelength range. TRAPPIST-1, at 40 light-years, is close enough to be accessible to ground-based telescopes. The extremely large telescope could observe TRAPPIST-1e in transmission during transits, or possibly even in emission, detecting heat radiation from the planet's day side. The giant Magellan telescope, also under construction in Chile, will have a 25-meter effective diameter. The 30-meter telescope, planned for Hawaii or Spain, will have, unsurprisingly, a 30-meter mirror. All three of these next-generation ground-based telescopes will be operational in the 2030s. All three will be capable of exoplanet atmosphere studies. TRAPPIST-1 will be a target for all of them. The combined power of these facilities, Webb in space and giant ground-based telescopes on Earth, plus dedicated missions like Pandora and Ariel, will create an unprecedented capability for studying exoplanet atmospheres. We're entering an era where we'll characterize dozens or hundreds of rocky planets, determining which ones have atmospheres, what those atmospheres contain, and whether any show signs of life. TRAPPIST-1 is the first, the pathfinder, the test case for all the techniques and technologies we're developing. But it won't be the last. There are other nearby systems with potentially habitable planets. Proxima Centauri, our nearest stellar neighbor at just 4 light-years away, has at least 2 planets. One of them, Proxima Centauri b, orbits in the habitable zone. LHS 1140, a red dwarf 41 light-years away, has a planet called LHS 1140b. It's larger than Earth, a sub-Neptune or possibly a water world. It transits, making it accessible to atmospheric characterization. Some models suggest it could be an ocean planet with a hydrogen-rich atmosphere. TOI 700. Another nearby system has a planet TOI 700d in the habitable zone. It's 100 light-years away, farther than TRAPPIST-1 but still accessible to Webb. Ross 128, 11 light-years away, has a planet in the habitable zone that might be detectable with future technology, even though it doesn't transit. All of these systems will be studied. All of them will teach us something about the diversity of rocky planets and the conditions that allow atmospheres to form and persist. TRAPPIST-1 is special because of its 7-planet system. 7 worlds to compare, all around the same star. It's a natural laboratory for understanding planetary evolution. Why did some planets lose their atmospheres while others might have kept them? What role does orbital position play? What about planet mass and composition? By comparing the 7 TRAPPIST-1 planets, we can answer these questions in ways that wouldn't be possible, studying planets around different stars. This is the broader context of the TRAPPIST-1 observations. We're not just studying 7 planets. We're developing and testing the methods that will be used to study thousands of planets over the coming decades. Learning what works and what doesn't. Understanding the limitations of our techniques. Pushing the boundaries of what's possible. And as we do, we're getting closer to answering that ancient question. Are we alone in the universe? This is what the TRAPPIST-1 story teaches us. Science doesn't move in great leaps. It inches forward through painstaking observation and careful analysis. 4 transit observations of TRAPPIST-1. Months of data analysis. 2 scientific papers presenting ambiguous results. No definitive answers. Just narrowed possibilities and hints that might or might not be real. It's frustrating if you want immediate answers. But it's how science actually works, especially at the absolute edge of what's technologically possible. We're attempting something that's never been done before. Characterizing the atmosphere of an Earth-sized planet in the habitable zone of a star 40 light-years away. There's no instruction manual for this. Every observation teaches us something new about how to separate planetary signals from stellar noise. Every analysis refines our techniques. Every paper, even those with ambiguous conclusions, moves the field forward. And here's the thing. We're going to get there. Maybe the next batch of TRAPPIST-1 observations will be definitive. Maybe it will take years more data from Webb and Pandora and future telescopes. But eventually, we will know whether TRAPPIST-1 has an atmosphere, and if it does, what that atmosphere contains. and whether those contents hint at something biological. This is the most exciting time in the history of astronomy. For thousands of years, humans have looked up at the stars and wondered whether we're alone, whether other worlds exist, whether life is out there somewhere. Now, for the first time, we have the tools to actually find out. We're not just wondering anymore. We're looking. We're measuring. We're analyzing data from real planets around real stars. TRAPPIST-1e might turn out to be a frozen, airless rock, or it might be a hazy water world with an atmosphere that hints at biology. Either result is profound. If it's airless, we learn that habitable zone planets around red dwarfs struggle to maintain atmospheres. That would tell us something fundamental about where life can exist in the universe. If it has an atmosphere, especially one with methane, we learn that these planets can survive the radiation bombardment from their stars. That would open up billions of red dwarf stars as potential hosts for habitable worlds. And if that methane turns out to be a biosignature produced by life, that changes everything. But let's step back and think about what standing on TRAPPIST-1e would actually be like. Assuming it has an atmosphere, assuming it's habitable, what would you experience? First, the sky. TRAPPIST-1, the star, would dominate the heavens. From the surface of TRAPPIST-1e, the star appears about 2.17 degrees across. That's roughly 4 times wider than our Sun appears from Earth. Our Sun is about half a degree across in our sky. TRAPPIST-1 would be this enormous dim orange disk hanging in the sky. Orange, not yellow like our Sun, because red dwarfs emit most of their light in the infrared and red wavelengths. If you were standing on the day side of this tidally locked world, that orange sun would never move. It would hover in the same spot in the sky, day after day, year after year, century after century. Eternal day. On the night side, you'd never see the star. Eternal night. But remember, with an atmosphere, heat would be redistributed. Winds would carry warmth from the day side to the night side. The terminator, the boundary between day and night, might be the most habitable region. Not too hot, not too cold. A permanent twilight zone. And the other planets. From TRAPPIST-1e's surface, you'd see the other 6 planets. They orbit so close to each other that they'd be visible to the naked eye. Not as pinpoints like we see planets from Earth, but as actual disks. TRAPPIST-1f, the next planet out, would appear larger in TRAPPIST-1e's sky than our moon appears from Earth. You'd see it as a world, not just a dot. TRAPPIST-1d, the next planet inward, would be even larger. Depending on where each planet was in its orbit, they'd wax and wane like our moon. You'd see crescents, half phases, full disks, and they'd move noticeably across the sky over the course of hours and days. The inner planets would retrograde, appearing to move backwards at times due to the complex orbital mechanics. It would be a spectacular sky. Multiple worlds visible at once, some of them potentially habitable, like your own, hanging in the heavens like lanterns. If any of those other planets had life, civilizations looking up at their sky would see you too. Multiple inhabited worlds in the same system, all visible to each other. It's a science fiction scenario, but it's physically possible. The TRAPPIST-1 system's tight configuration makes it uniquely suited for this. Now, think about the environment. TRAPPIST-1e receives 60% the stellar flux Earth does. That's more than Mars, which receives about 43%. Mars is cold, with an average surface temperature of -81 degrees Fahrenheit. But Mars also has a very thin atmosphere that provides almost no greenhouse warming. TRAPPIST-1e, with a proper atmosphere, could be much warmer despite receiving less light than Earth. Venus receives nearly twice the stellar flux Earth does and has a surface temperature of 860 degrees Fahrenheit. That's hot enough to melt lead. Venus demonstrates how powerful greenhouse warming can be. TRAPPIST-1e won't be that extreme, but with the right atmospheric composition, it could maintain temperatures well above freezing. Liquid water could exist. If TRAPPIST-1e is indeed a water world with a global ocean, that ocean might be quite deep. Remember, the planet's low density suggests a high water content. If 20% of TRAPPIST-1e's mass is water, that's about 150 times more water than in all of Earth's oceans. That water could be distributed as ice in the interior, water vapor in the atmosphere, and liquid water on the surface. A global ocean, several tens of miles deep, is possible, deeper than Earth's deepest ocean trenches. With no continents, no land masses, just water stretching from horizon to horizon. An ocean world. On Earth, life originated in the ocean. The first cells appeared in water roughly 3.8 billion years ago. For billions of years, life existed only in the ocean. Land was barren. It wasn't until about 500 million years ago that complex life moved onto land. An ocean planet like TRAPPIST-1e, if it has life, might be similar to early Earth. Life in the water, nothing on land. Microbes, perhaps simple multicellular organisms, but no trees, no animals, no cities. Just an endless ocean beneath an orange sky. But let's not get ahead of ourselves. We don't know if TRAPPIST-1e has water. We don't know if it has an atmosphere. We don't know if it's habitable. We're still at the stage of trying to answer the most basic question. Is there air on this world? Everything else, the speculation about oceans and life, and what it would be like to stand there, is premature. But it's worth thinking about. Because if Webb's next observations confirm an atmosphere, all of those scenarios become real possibilities. The broader implications of the TRAPPIST-1 observations extend far beyond one system. Red dwarf stars make up about 70 to 75% of all stars in the Milky Way. There are somewhere between 200 to 400 billion stars in our galaxy. That means there are roughly 150 to 300 billion red dwarf stars. Each one could potentially have planets. And because red dwarfs are small and cool, their habitable zones are close in. Close-in planets transit more frequently. They're easier to detect and study. This makes red dwarf planets the most accessible targets for atmospheric characterization. If we want to find life on exoplanets within the next few decades, red dwarf systems are where we'll most likely find it. Not because life is more common there, but because those systems are easier to study. But there's a catch. Red dwarfs are violent when they're young. And even old red dwarfs like TRAPPIST-1 produce regular flares. These flares release enormous amounts of high-energy radiation. X-rays, ultraviolet light, energetic particles. This radiation can strip away planetary atmospheres over time. It can also damage biological molecules, making the surface of these planets hostile to life. On Earth, we're protected by our magnetic field and atmosphere. The magnetic field deflects charged particles from the sun. The ozone layer absorbs ultraviolet radiation. We're shielded. But TRAPPIST-1e might not have a magnetic field. Small planets lose their internal heat faster than large planets. Earth's magnetic field is generated by convection in our liquid iron core. If TRAPPIST-1e's core has cooled and solidified, it wouldn't have a magnetic field. Without that protection, stellar radiation could be a serious problem. Even with an atmosphere, the surface might be bathed in dangerous levels of ultraviolet light. Life, if it exists, might be confined to the oceans. Deep underwater, shielded from radiation, microbes could thrive. But the surface might be sterile. This is one of the big unknowns about red dwarf habitability. Can life survive the radiation environment? Some scientists argue that life would adapt. Earth's early atmosphere had no ozone layer. Life evolved in the oceans, protected by water. Only later, after photosynthetic organisms produced oxygen, and that oxygen formed an ozone layer, did life move onto land. TRAPPIST-1e could follow a similar path. Ocean life first, surface life later, after an ozone layer forms. If it ever does. Other scientists are more pessimistic. They point out that red dwarf flares can be incredibly powerful. Some flares release energy equivalent to billions of nuclear bombs. These superflares could sterilize planetary surfaces, and they happen regularly. TRAPPIST-1 produces flares energetic enough to affect transit observations multiple times per day. Smaller flares are even more frequent. A planet bathed in that level of radiation for billions of years might struggle to develop and maintain life. The TRAPPIST-1 observations are testing these competing hypotheses. If we find that the planets have atmospheres, it suggests those atmospheres can survive despite the radiation. That would be encouraging for red dwarf habitability. If we find that the planets are airless, it suggests the radiation wins. Atmospheres are stripped away, and these planets can't be habitable. This is why every observation of TRAPPIST-1 matters. We're not just learning about 7 planets around one star. We're learning about the potential habitability of hundreds of billions of red dwarf systems across the galaxy. There's another aspect of the TRAPPIST-1 story worth considering. The role of time. TRAPPIST-1 is 7.6 billion years old. Our Sun is 4.6 billion years old. TRAPPIST-1 formed 3 billion years before our Sun. 3 billion years is an enormous span of time. On Earth, 3 billion years ago, life existed, but it was microscopic. Only single-celled organisms. No plants, no animals, nothing visible to the naked eye. Fast forward 3 billion years to today, and Earth has forests, whales, humans, civilization. If life emerged on TRAPPIST-1e at the same time it emerged on Earth, roughly 3.8 billion years ago, it's had an extra 3 billion years to evolve. On Earth, complex multicellular life didn't appear until about 600 million years ago. Intelligence evolved only in the last few million years. Civilization in the last 10,000 years. What could life accomplish with an extra 3 billion years? It's impossible to say. Evolution doesn't follow a predictable path. Intelligence might be extremely rare, a fluke that happened on Earth but nowhere else. Or it might be common, arising on many planets given enough time. If intelligence is common, And if TRAPPIST-1e had 3 billion extra years, there's a non-zero chance that planet could have technological civilization. Think about that. A world 40 light-years away, visible to the naked eye from Earth, if you know where to look, potentially inhabited by intelligent beings. They'd see Earth in their sky, a dim point of light orbiting a yellow star. If they had telescopes, they could study us the same way we're studying them. They'd see Earth as it was 40 years ago. 1986. The Challenger disaster. Chernobyl, the height of the Cold War. Our radio and television signals from that era are reaching them now, traveling at light speed, spreading outward as a sphere centered on Earth. They might be listening, analyzing our broadcasts, trying to decipher our languages and culture. Or maybe not. Maybe TRAPPIST-1e is barren. Maybe it's an airless rock. Maybe life never emerged there, despite billions of years of opportunity. Or maybe life emerged, but stayed simple. Microbes and nothing more. We tend to imagine exoplanet life as either microbes or advanced civilizations. But most of Earth's history featured multicellular life that wasn't intelligent. Forests and oceans full of creatures, but no one building telescopes. TRAPPIST-1e could be at that stage. Teeming with life, but pre-intelligent. No one looking back at us. Or maybe intelligence arose, but that civilization is gone. Self-destructed, or wiped out by a natural disaster, or moved elsewhere. Ruins beneath the oceans, monuments on the seafloor, but no current inhabitants. The possibilities are endless. And right now, we can't distinguish between them. We're still trying to figure out if there's air. One more thing worth discussing: the sheer improbability of what we're attempting. 40 light-years is close in astronomical terms, but it's still mind-bogglingly far in human terms. 40 light-years is 235 trillion miles. To put that in perspective, the farthest human-made object, Voyager 1, launched in 1977, has traveled about 15 billion miles. It's been traveling for almost 50 years. At that rate, it would take roughly 660,000 more years to reach TRAPPIST-1. 660,000 years. Modern humans, Homo sapiens, have only existed for about 300,000 years. Written language has existed for about 5,000 years. Civilization as we know it, with cities and agriculture, for maybe 10,000 years. The time it would take to physically reach TRAPPIST-1 with current technology is longer than all of recorded human history. Many times longer. This distance is not something we can physically cross with foreseeable technology. Not in our lifetimes, not in many generations, possibly not ever. The laws of physics impose limits. Nothing can travel faster than light. Even if we developed spacecraft that could reach 10% the speed of light, which would require technology far beyond anything we have, the trip to TRAPPIST-1 would take 400 years. 20 generations. They would have been born, lived, and died on that spacecraft, never seeing Earth or the destination. This is the reality of interstellar travel. The distances are too vast for chemical rockets or even nuclear propulsion. You'd need something exotic, like antimatter engines or light sails pushed by powerful lasers, technologies that exist only in theory. So the only way we can study TRAPPIST-1 The only way we'll ever know what these planets are really like is with light. Electromagnetic radiation traveling across the vast gulf between us. Photons emitted by TRAPPIST-1 40 years ago, carrying information encoded in their wavelengths, arriving at Earth and being collected by a 6.5-meter mirror floating in space 1,000,000 miles from our planet. Those photons pass through a complex series of mirrors, filters, and gratings, being sorted and analyzed. Computer algorithms process the data, removing noise and instrumental effects. Scientists spend months or years interpreting the results, all to answer one question. What is that distant world like? The fact that this works at all is miraculous. Think about what's actually happening. A photon leaves TRAPPIST-1's atmosphere 40 years ago. At that moment, Jimmy Carter is president. The Soviet Union still exists. Personal computers are just becoming available. The internet doesn't exist yet. That photon travels through space for 40 years. Undeflected, unabsorbed, crossing the empty darkness. It arrives at Earth in 2025. The world has completely changed. But the photon carries information from 2085, encoded in its wavelength. Maybe it was absorbed and re-emitted by a methane molecule in TRAPPIST-1's atmosphere. That absorption shifted its wavelength slightly, by a tiny fraction. Webb's detectors measure that shift. Algorithms analyze thousands of similar photons, building up a spectrum. Scientists interpret that spectrum, determining what molecules cause the absorption. And from that, we learn whether TRAPPIST-1 has air, whether it might have water, whether it could support life. All from photons that left that world before most people watching this were born. The fact that we can say anything meaningful about the atmospheric composition of a planet hundreds of trillions of miles away, based on the tiny fraction of light we collect, is a testament to human ingenuity. We've built the tools. We've developed the mathematics. We've created the techniques. We've trained ourselves to think in ways that make this possible, to extract signal from noise, to model atmospheres and predict spectra, to design instruments sensitive enough to count individual photons and measure their wavelengths with extraordinary precision. And now we're using all of this, the culmination of centuries of scientific progress, to explore worlds we'll never visit in person. This is what science fiction imagined. Telescopes so powerful they could study distant planets. Instruments so sensitive they could detect the chemical composition of alien atmospheres. Except, it's not fiction anymore. It's happening. Right now. Today. As you watch this, James Webb is somewhere in space, orbiting the Sun, collecting photons from TRAPPIST-1 and other distant stars. Computers are processing that data. Scientists are analyzing the results. And slowly, bit by bit, we're figuring out what those worlds are like. There's something profound about this moment in history. For most of human existence, the stars were unreachable. Pinpoints of light in the night sky, beautiful, but forever beyond our grasp. We could look at them, wonder about them, tell stories about them, but we could never touch them. The invention of the telescope in the 1600s changed that. Suddenly, we could see that the stars weren't just points. Some of them had moons, rings, clouds. They were worlds. The invention of spectroscopy in the 1800s changed it again. We could analyze the light from stars and determine what they were made of. Iron, helium, hydrogen, calcium, the same elements we find on Earth. The universe wasn't made of some exotic cosmic substance. It was made of the same stuff we are. The discovery of exoplanets in the 1990s changed it once more. Planets weren't unique to our solar system. They were everywhere, orbiting other stars, countless worlds waiting to be discovered. And now, in the 2020s, we've reached another milestone. We're characterizing the atmospheres of Earth-sized exoplanets, determining what they're made of, searching for signs of habitability and life. We've gone from looking at distant lights to analyzing the air on distant worlds in just a few centuries. The pace of progress is staggering, and it's accelerating. Webb launched in 2021. Already, it's revolutionizing our understanding of exoplanets. Pandora launches in 2026. Ariel in 2029. Ground-based giant telescopes in the 2030s. The Habitable Worlds Observatory in the 2040s or 2050s. Each generation of instruments more powerful than the last. Each one answering questions the previous generation could only ask. Within our lifetimes, possibly within the next decade, we might find definitive evidence of life beyond Earth. Not little green men visiting in flying saucers, but chemical signatures in the atmosphere of a distant planet. Molecules that shouldn't be there unless biology is producing them. That discovery, when it comes, will change everything. It will tell us that life is not unique to Earth, that wherever conditions are right, life emerges, that the universe is full of living worlds, perhaps billions of them in our galaxy alone. It will answer the question that every human culture has asked since we first looked up at the stars and wondered, are we alone? And the answer will be no, we're not. Life exists elsewhere. We're part of a living universe. Or maybe the answer will be yes. Maybe we'll study hundreds of potentially habitable planets and find none of them have signs of life. Maybe Earth really is special, unique, the only world in the observable universe where life has emerged. That answer would be profound too. It would tell us that life is incredibly rare, that we're extraordinarily lucky to exist, that we have a responsibility to preserve the only life we know of. Either answer changes our perspective on our place in the cosmos. Either answer is worth seeking. This is why TRAPPIST-1 matters. It's not just about one planet around one star. It's about understanding our place in the universe. It's about answering questions that humans have been asking for thousands of years. It's about pushing the boundaries of what's possible with science and technology. It's about looking up at the night sky and knowing that we're not just wondering anymore. We're finding out. We're collecting data, analyzing it, publishing results. We're turning speculation into knowledge, philosophy into science, dreams into reality. And that's extraordinary. The TRAPPIST-1 system sits 40 light-years away in the constellation Aquarius. Light that left those planets when you were born is just reaching Earth. Now, if you're 40 years old, we're seeing TRAPPIST-1 as it was in 1986. If there's life on that planet looking back at us, they're seeing Earth as it was in 1986. James Webb is collecting that ancient light and breaking it into spectra, reading the secrets encoded in wavelengths and absorption lines, asking, does this planet have air? Does it have water? Could it have life? And for the first time, we're getting answers. Not definitive ones yet, but real data that's narrowing down the possibilities. We know TRAPPIST-1 doesn't have certain types of atmospheres. We know it might have others. We have tentative hints of methane that could point to something extraordinary. The next year or two will be crucial. 15 more Webb observations are underway. By comparing TRAPPIST-1's transits with TRAPPIST-1b's, astronomers will separate stellar contamination from real planetary signals. Pandora will launch in early 2026 and begin monitoring the star's variability. New papers will be published. New results will be announced. And with each observation, the picture becomes clearer. Maybe we'll confirm that TRAPPIST-1 has an atmosphere with methane. Maybe we'll find that the methane is produced by intense volcanic activity. Or maybe, just maybe, we'll find that it's biological, produced by living organisms on a world 40 light-years away. Or maybe we'll discover that TRAPPIST-1 is airless after all, that the methane signatures were stellar contamination, that this world, like the inner TRAPPIST planets, lost its atmosphere long ago. But even that would be valuable. It would tell us where to focus our search. Which types of planets can hold onto their air, where life is most likely to arise. Right now, we're in that exciting space between discovery and confirmation. We have hints, intriguing data, possibilities that make scientists stay up at night running calculations and planning observations. TRAPPIST-1 might be a barren rock, or it might be an ocean world with a hazy methane atmosphere and liquid water in the twilight zone between eternal day and eternal night. It might even harbor life. We don't know yet, but we're closer to finding out than we've ever been. Thanks for staying with me through this journey into one of the most important scientific investigations of our time. The story of TRAPPIST-1 is still being written. Over the next few years, as more observations are completed and analyzed, we'll learn the truth about this world 40 light-years away. And whatever we find will reshape our understanding of planets, atmospheres, and the possibilities for life in the universe. The fact that we can even ask these questions is extraordinary. That we can collect light from a planet orbiting another star and determine whether it has methane in its atmosphere. That we're on the verge of potentially discovering signs of life beyond Earth. That's what makes this the most exciting time in the history of astronomy. The answers are out there, written in starlight, encoded in spectra, and we're learning to read them.